Hello, my name is Cliff Goldstein. I'm with Eclipse Engineering. We're a manufacturer of seals and different types of polymer profiles. Today we're going to have a discussion on rubber energized seals, but we're going to start with some basics. We're going to basically cover how seals perform, what it takes to do seals, and we're going to end up with rubber energized elements like urethane or PTFE or Teflon. A little background: Eclipse Engineering, we design and manufacture high performance polymers. We make a variety of different types of seals, specifically rubber energized seals, spring energized seals, and rotary seals. And today our focus, as we've stated, is going to be around how rubber energized seals work. So the first thing that we want to discuss is some seal considerations. And whenever we go into the design process, we ask ourselves, what are the criteria that are going to decide what a seal is going to look like? So I start off with cost being number one, because if we're into the automotive industry, typically these seals are low cost, and we've got to find a way to keep our dollars down. We look at things like the pressure, the system pressure, the types of fluids that are involved, the exterior environment. In other words, are we going to be operating in very cold temperatures or very hot temperatures? So temperature has a great big impact, or a large impact. Friction is another area. Is friction important in the application? And to what level is friction important? Finally, again, I mentioned briefly before, but fluids are important. Are we going to be sealing gas or a liquid? And will that fluid remain at one viscosity, or will it be changing viscosities? And finally, if you'll notice on the slide, there's two signs there that say cost. And oftentimes, we'll start off a lot of our discussions with engineers, and cost is no factor, but we know that cost always enters into the formula. When we're looking at seals for customers, we always have to evaluate the cost in the process of putting these seals in. And so when we design or develop seals, we always try and start off with, will an O-ring do the job? And that's the way you should look at seals when you're putting them in customers' hardware. Putting in seals that are very expensive and are not necessary doesn't really solve the customer's problem, and you drive the cost up of his hardware, and especially if an O-ring will do the job. So we always start off when we're faced with an application, we ask ourselves, what's the least expensive, most effective seal without giving up performance? And so we look at O-rings. So in static lands, we typically find O-rings. If it's not too dynamic, we'll use quad rings or X rings. U-cups are a standard seal. You'll find them, everywhere in the marketplace. Radial lip seals fit in there, and then we get into the higher performance materials like the cap seal or the buffer ring. These types of PTFE O-ring energized style seals, and they're certainly higher cost than most of these others. Finally, we move into spring energized seals, where the costs are getting even greater, and then rotary cased spring energized seals and rotary seals, and finally, what's not shown there are mechanical seals. So when we look at a customer's application, we consider these elements as we're going up the decision tree as to what direction we should be going for the style of seal. I don't think that we should ever give up performance, but if an O-ring will give the same performance as a rubber energized Teflon seal, we should just be putting an O-ring in. But if friction is of a concern, these other seals aren't going to cut it. We'll end up putting in something like a rubber energized or even a spring energized seal, depending on what the customer's requirements are. Another consideration in the design is PV, or pressure velocity. Pressure velocity is simply multiplying two numbers together, pressure and PSI, and velocity in feet per minute. Most of the materials that we use for sealing have limits to what those numbers are. There's some Teflon elements that will go up to 500,000 PV, where most elastomers are much, much lower than that. So, and it's irrelevant of whether it's reciprocating or rotary. PV comes into play. If you exceed the PV limits of the mating materials, they will fail prematurely, so we need to be very cognizant of that as we're in the design phase of selecting a seal for a customer. The examples here are how to calculate PV. I'm not going to go through them, but it's a very simple calculation. But PV is very important, and these numbers, PV limits, are available for all materials that we use for sealing. This is a seal selection chart, and it helps you to, or guides you through selecting the kind of seal you're looking for. And you'll notice that rotary motion, you'll see PV is greater than 100,000. That we use some special items to keep the seal stationary. But for rubber lip seals, you'll notice that we need to keep the PVs much lower, or else we'll begin to spin in the hardware. So we're trying to we use these to help us decide what the seal is actually going to look like. Considerations are, of course, pressure, temperature, fluids. So even though we have PV, we need to throw in all these other factors. And we have to remember that as we move quickly, or as the hardware is moving faster and faster, we generate more heat. That's not really a consideration in PV, but if we drive a lot of heat into the system, we will cause the seal to prematurely fail, even though we didn't exceed the PV, because these PV limits are done at room temperature around 70 degrees Fahrenheit. I'm going to switch gears on you a little bit. One of the elements that is found in all piston and rod type seals are bearings. Bearings are crucial to allowing seals to perform properly. If we can't keep the hardware centered, if we can't keep the rod centered in the rod gland, or the piston centered in the bore, we're asking the seal to perform these functions. Somehow or other we have to guide these elements, and so we'll make different types of rod or piston wear rings. This one here is depicted as a rod wear ring. They can be made out of a lot of different materials. For low loads, or where there's not a lot of side loading, PTFE or filled PTFE elements work great. When the loading gets very, very high, we have some polyester materials that can handle loads as much as 50 times higher than what the PTFE elements will handle. I'm going to bring up an application for a wear ring. And here's a case where we had a wear ring in an application that was out of PEEK, which is also a wear ring type material. However, this is where material becomes very, very important. The material was wearing the rod out. It was pharmaceutical, so there was powder getting underneath the PEEK, and those two materials were becoming very abrasive on stainless steel rods. In this particular customer's case, these rods were 8 feet long and 4 inches in diameter. We came back and replaced it with a polyimide-filled PTFE split bearing. We solved the wear on the shaft, and even though the loading of the Teflon element didn't handle nearly as well as the PEEK, in this particular application, the PTFE elements were more than sufficient to take care of the load at a lower cost to the customer without having to replace an 8-foot long stainless steel shaft. So materials are very, very important. This is a piston seal bearing assembly, and you can see that I'm depicting two bearings on both sides of a piston style seal that's O-ring energized. The purpose of the bearings, as I described before, is to keep that piston centered in the bore. Depending on the diameters, we may do it with one bearing, or we may do it with two, or depending on how bad or how much loading we have, we may use a combination of bearings. If we split bearings, as we're seeing in this picture here, what we're doing is we're not putting all the loading on one side. We basically keep the piston balanced in the bore. With very short pistons, that's not available, but if we can split the bearings, we're better off because we keep we don't allow that piston to rock inside the bore. This is a typical rod sealing application, and we talked about the dual elements. You're looking at a dual buffer rings in this particular case. The fluid is coming from the right side of the picture, and the fluid is then energizing the buffer rings. You notice that we put a bearing in between the two buffer rings. That bearing will be lubricated because we know that the first seal will leak a little bit. The second seal being either some kind of elastomer type element or even a U-cup will be the mop-up or the zero leak element. Pressure in between the two seals will be roughly 100 psi. In this particular application, you'll notice that there's another bearing behind the second buffer ring or behind the second U-cup, and the purpose of that bearing, again, is to help stabilize the rod. There's a third element in there. We're not going to talk a lot about it, but it's a wiper. Wipers are critical, especially in dirty applications. Couple of the features that'll wear a seal out very quickly, of course, are friction and heat, but dirt is also another large contributor to the failure of sealing elements. And so we try and keep the level of dirt out of these systems using wipers. And finally, this is just a cross-section of the two seals in place, which creates a near-zero leak system. That second element, oftentimes customers will just have a urethane U-cup, but under high load, that urethane U-cup with high cycle rate and high pressure, 3,000 psi, 2,500, 3,000 psi, that urethane U-cup will typically wear out rather quickly. When we put the buffer element in front of it, we extend the life of that U-cup to at least as long as that PTFE or that buffering, the Teflon element. We've extended the life of the urethane elements by 3 and 4 times its standard life by putting that PTFE element in front of it. Finally, these are the rod scrapers. I talked about it briefly. Rod scrapers are used to keep dirt out of a system. It's important to keep the dirt out. I mentioned it earlier. And there's a lot of different varieties of how we make these rod wipers, but they are important in keeping the system clean. This is just one version. There's probably a half a dozen versions that we use depending on the customer's hardware and the type of dirt we're trying to exclude and how much loading we can put onto the shaft. Again, all of these elements create friction, and so we need to be very careful about what kind of elements we're putting in. Lots of different materials to work from. This is I'll call this the short list, and you'll notice up on top is PTFE or Teflon. We do use some virgin grades, but typically we fill PTFE with a variety of materials, things like carbon, graphite, polyimides, bronze, stainless steel. There's also different types of PTFEs that we can use that have better strength characteristics, like TFM, which is a copolymer, or PFA, which is an injection moldable PTFE. Some of the other materials we use for backup rings, things like PEEK or nylon or Delrin, acetals. Urethanes, of course, are good secondary seals. Briefly, the rubbers are out of a variety of materials, which I'm not going to cover here today. UHMW is another common material, although not used as much in hydraulic systems, but in air systems. UHMW is an excellent seal material. Hytrel or thermoplastic elastomers. For low temperature, we have PCTFE. PVC is normally used for installation tools. Some high temperature materials like Torlon, Altem, Riton is a good bearing material. I mentioned polyimide or Vespel as a filler as well as out of a seal material. Material that we've never used is Solazol, but it's available. I talked about high load bearing materials. That would be a polyester resin fabric composite, which is capable of 50,000 psi loading, where Teflon has about 1,000 psi. These are bearing grade type materials. And then finally, just carbon face seals, this sort of thing. That ends the presentation. If you have questions, please feel free to contact your local distributor, or of course you can contact Eclipse Engineering. And thank you very much for listening.